Pointers are a frequently confusing topic for intermediate computer science students. A misunderstanding about the arithmetic surrounding pointers, or even the very nature of what a pointer is a significant barrier to students that need to code in C or C++, or do tasks with large datasets that need to be efficient. By the end, you'll have a working understanding of pointers and how to modify them with math. Simply put, a pointer is a location in memory. Sure, when you print a pointer out, it's a hexadecimal number that looks like this, but you can think of it as a big arrow or a highway sign telling you where to go find something. In code, pointers are often declared like this. The important thing to pay attention to is the inclusion of the asterisk. Next, call the malloc function to ask the computer to give you a location in memory of a certain size in bytes. But be careful, different types can be different sizes in bytes, so malloc calls are often done like this. Since the function sizeOf returns the number of bytes in a given type, multiplying like this is the equivalent of asking for a pointer to a chunk of memory large enough to fit n of a given type. In the code example, some variable is now a pointer to a chunk of memory that can store 2 integers, and another variable is a pointer to a chunk of memory that can store 3 characters. Now, if you try printing out the variables, the output will look like this, which can be confusing because the 2 pointers look exactly the same, and to make it momentarily even more confusing, they look the same because they are the same. Pointers, no matter what, are just locations in memory. The differing types, like int and char, are there to inform the programmer what is present at the location in memory being pointed at. No matter the associated types, a pointer will always indicate a point in memory where you can go to and find something. To explain this further, we're going to talk about street addresses. For this example, the house we're going to look at is on Sycamore Street, with the house number of 88. So, the street address for the house can be written as 88 Sycamore Street. To lean on pseudocode a bit, what we've done here would look like this in code. Notice how printing the house pointer prints out the street address, similarly to how earlier printing out the code pointer printed out a memory address. Also, similar to how you can share the house address around and always be sure that it refers to the same location, the same is true for pointers in computer code. 88 Sycamore should always refer to that location. A memory pointer is the same. Now, for the concept of different types. Street addresses aren't used to exclusively refer to houses. For example, let 89 Sycamore Street refer to a school. Again, similar to pointers, notice that printing the street address for the school looks exactly the same. It doesn't matter that the street address is referring to something different. You would only know the difference by the type annotation, or actually going to the destination. The question remains, why use pointers in the first place? The examples so far haven't been convincing. Rather than have a pointer to an int, why not just have an int variable? The reason why this doesn't make sense is because pointers often refer to a sequence of a given type, rather than just one instance. In this code, we allocate a space that can hold 10 ints. You might be wondering, how is this different from a list? The difference is in how lists and pointers get passed around in functions. Depending on the language implementation, lists can get duplicated and copied as they get passed in as different arguments to functions. Pointers will always have that memory address just passed around. This becomes really important when you're dealing with code that needs to be fast. A good example are video game rendering engines or anything that deals with images. A 1280 by 720 video frame with RGBA encoding can be represented as a sequence of 3,686,400 numbers. I have another video on how this is possible here. If you use a list as an argument to a function, the computer needs to allocate the memory, which is one of the most expensive operations you can do, and copy the data every single time the function is called. That would be like having to allocate a plot of land and build a house every single time you wanted to tell someone about a house. It just takes too long. Instead, you can just point to the location and make things much faster and more efficient. In fact, you're probably using pointers in your code already without even knowing it. If you pass in an object to a function, then change a value on that object, have you noticed that when you go back to the original calling function that the value remains changed? That's because the language you're using passed the object around as a pointer to save what would be a potentially expensive operation of allocating and copying to get a new object. This is all well and good in the abstract, so let's quickly take a look at video games for a practical example. First, starting a game and loading takes so long because that's when the expensive memory allocation and copying steps take place. As you load from one level in a game to another, all the assets for that next level get loaded from the disk into memory. This allows the assets to have a pointer assigned to them that can be used later. This looks like the malloc call from earlier, but much larger. This is why modern games use so much RAM. They need to load their large assets from memory for use later. Having the data in memory and those pointers are how frames can be generated so quickly. Instead of having to do the slow, expensive operation of allocating memory and copying the asset from disk, the game can instead quickly use the pointer to access that asset where it already is loaded into memory to render the frame. The initial pointer only points to the beginning of the allocated space, so var is only pointing at the beginning of the allocated section. Pointer math is how you access the remaining 9 locations. Since the memory allocated is sequential, we can access the next block of memory by adding to the pointer. Pointer math functions on bytes, so adding the number of bytes an integer takes up to the pointer advances the pointer enough in memory to point to the next available spot for an integer. This is what it looks like in actual numbers. In this code, hex number 2AADB39F is the location of the first int, and assuming that int is size of 4, adding 4 to the location brings you to the second int, and you can keep incrementing the pointer to access the next slots and so on and so forth. When incrementing pointers, it's important to keep track of the size of the data you're working with. In the example, the size of int was 4. However, incrementing a pointer isn't as simple as adding 4 every single time. Different computers have different sizes for int, so it will always be more accurate to have the code read var plus size of int. This way, all kinds of computers are accounted for. Additionally, different data have different sizes, so it's critical to increment by the appropriate amount. Let's look at the following code for y. If we aren't careful, we can increment the int pointer by too much and skip some of the data. Alternatively, if the roles were reversed, incrementing by an inappropriate amount would place you in the middle of a double, which would make the information you're programming is parsing nonsense. Now, there is some hope for this complicated mess. Some programming languages provide niceties that allow you to access elements in a pointer using list-like syntax and increment using ++. So, you could access the second location with var square brackets 1 instead of having to manually increment the pointer. Similarly, if you wanted to permanently update the pointer, you could use ++ instead of var equals var plus size of int. When you're using pointers, even if you're diligent about sizes, you still have to be careful how much you increment. Even though we only allocated for 10 ints, we can keep adding to the pointer and start to access sections of memory outside of the allocated location. This will cause the program to do unexpected things and can be a security vulnerability. Pointers aren't restricted to pointing at ints and objects. Pointers are just memory addresses, so they can point to functions and even specific lines of code. When a computer program is loaded into memory, each command is given a memory address. This address is then used to facilitate operations like calling a function or return. For example, when function 1 is called, the program jumps to the hex address for the first line of function 1 and starts executing. Then, when function 1 returns, the program jumps back to the hex address for print test and continues executing the program. Now let's look at a program with a vulnerability. Specifically, the vulnerability is on line 10 when gets user string is called. Gets is a method that takes user input from standard in and puts it in the given argument. However, it doesn't restrict the size of the input. So, even though user string can only store 10 characters, there's nothing stopping a user from inputting 10 or even 1,000. This allows a malicious user to start overwriting locations in memory after the area allocated for user string. Since the call to malloc only requested 10 characters, all a malicious user would have to do is provide 11 characters to the program to start modifying locations in memory they shouldn't have access to. With some careful tweaking of the input by the malicious user, this can be used to overwrite the memory address that the call to return is going to use on line number 11. That memory address could be modified to point at the never called function, and therefore calling it with no other lines in the code ever referencing it. In fact, notice the top line of the program, include United Standard header file. This is a standard C library that contains such functions as exec. At this point, being able to call a never called function is an irrelevant point because you can modify the memory address used by return to point to exec and just execute any program on the computer system. This vulnerability is called a stack overflow and was one of the top 10 vulnerabilities covered by OWASP. With all the doom and gloom out of the way, let's look at some fun real-life examples of stack overflows. The Pokemon Blue any% speedrun uses a stack overflow, technically an underflow, to complete the game in 1 minute, 18 seconds, and 893 milliseconds. The first thing the speedrunner PokeGuy does is corrupt his save. This then allows him to execute the overflow. In moving items and Pokemon around in his bag, PokeGuy is using the internal values of those items to write in memory. Compared to the earlier example, this is the user exploiting gets. By the end, he switched the what should happen when he exits the menu with the code that warps him to the Hall of Fame. Another famous speedrun that uses this sort of computer exploit is the Legend of Zelda Ocarina of Time Any % run that finishes in 3 minutes, 50 seconds, and 950 milliseconds. When the speedrunner Murphy is doing all sorts of flips in specific locations while picking up and dropping certain items, while holding the bomb and facing certain directions while going through Cookie Forest, they are performing a stack overflow exploit to modify the memory so that when the final dodge roll occurs, it sends him to the end of the game. The fun thing about these kinds of exploits is that if the user has the right items, they can go anywhere in the game or modify anything in memory. Using these same sorts of exploits to modify pointers, it's possible to give yourself all the badges, infinite rare candies, infinite fairies, or even just teleport you wherever. Speedruns just have a specific goal in mind, which makes those cases not as useful. All that is to say, this is all possible by manipulating pointers and using them to modify the data they are pointing to. Now for the recap. Pointers are references to specific chunks of memory that data can be found at. This functions in the same way that street addresses do for houses. If you add 1 to a pointer, you move forward 1 byte. However, many primitives and objects are larger than 1 byte in size. So, you need to be careful to increment your pointers by size of type times the number of spaces you want to move forward. The same applies if you're going backwards with subtraction. By changing data at the other end of a pointer, all subsequent use of that pointer will be to the modified data. This is a powerful tool for program efficiency, but it is also the source of security vulnerabilities. So, it's important that pointers are used with proper care and proper testing. For more information about stack overflows and how to prevent them, visit the OWASP page down in the description. They refer to the bug by the name of buffer overflow. I hope that this video was able to clarify the often confusing topic of pointers. If you have any questions, please comment down below and I'll do my best to answer them. Thank you and have a wonderful day.